In this video, we're going to look at the conjecture that we had at the end of the last video, which is that when we compose a permutation with a transposition, the parity changes. So we're going to get started by looking at letting gamma be our transposition. We will write it as A goes to B. We are going to assume that A is less than B, since the two-cycle written A goes to B is the same as the two-cycle B goes to A. So we can always assume that alpha is written in the form where the lower number is first. We're going to let alpha be any permutation inside Sn, and it's important to realize that this means that there does exist a C such that alpha of C is equal to A, and there exists a D such that alpha of D is equal to B. Now, we don't happen to know if C or D, which one of those is bigger, so we're going to wind up with two cases. And the two cases are going to be C is less than D and C is bigger than D. We are going to work on this case in the video. Case 2 will be part of your homework. And what I want to notice is that the basic idea in trying to deal with how we look at the how the parity changes is we're going to essentially be looking at the idea that if we use this notation for the inversion number, the inversion number of first do alpha, then do gamma is essentially going to be the number of inversions in both of the permutations. Take away the inversions that appear only in alpha, and then we have to add back the number of inversions that appear only in first do alpha, then do gamma. So we kind of need to look at different sorts of inversions and what happens in the two different permutations. So the first thing is we're going to need to look at getting the two-row notation. Well, since we're assuming that C is less than D in case 1, if this is our two-row notation for alpha, to get the two-row notation for first do alpha, then do gamma, all we have to do is switch the order of those two elements. So this turns out to be the two-row notation for first do alpha, then do gamma. And again, you'll notice all I did was switch the two elements. Now, the neat thing is by looking at the permutation, when we start looking at inversions, there are several different things can happen. And if we look at an inversion that does not involve A or B, that means the inversion involves things that are in these chunks that I'm underlining in green. And I'm going to actually box these things in. And what I want to notice is that the order of the stuff in the green boxes is exactly the same. So if I star I double star is an inversion in alpha, so I star is here in both of them maybe, and I double star is here. What's important is that both of them are in part of the green. They're in the wrong order up here, so they're also in the wrong order down here. So this particular ordered pair is an inversion in alpha if and only if that same ordered pair is an inversion in first do alpha, then do gamma. Now what this means is that the only inversions we need to worry about are those that involve A or B. So let's look at that. We're now going to focus in on inversions that involve at least one of these two guys. And we're going to note in passing that since we already know that A is less than B, the ordered pair BA is an inversion in first do alpha, then do gamma. So we're not even really going to worry too much about him. Now, what I also want to notice is this. If I take some element out in this part of the second row, this particular ordered pair, IA, it's either an inversion or not up here, but if it's an inversion up here, then that same IA is an inversion down here. And if IA up here in alpha is not an inversion, then IA down here is also not an inversion. So for things over here, with A, we have IA is an inversion in alpha if and only if IA is an inversion inside first do alpha, then do beta. Now, on this particular thing, I also want to notice the same thing happens with B. If this I and that B are an inversion up there, this I and this B are an inversion down here. So what that means is that we also have for here that for these purplish blue things, if IB is an inversion in alpha, that's going to happen if and only if IB is an inversion in first do alpha, then do beta. Boy, my handwriting is getting awful. Let's see if I can make that at least a little bit more readable. Now, the other thing that I want to do is I want to look at the things out here, and I'm going to notice it's the same kind of an argument. If I have a J out here, if this A and that J is an inversion inside alpha, then this A and this J is going to be an inversion inside of first do alpha, then do gamma. So that ordered pair will also be an inversion in first do alpha, then do gamma. And the same kind of thing happens with B. If this B and that J is an inversion up here in alpha, then this B and that J is an inversion down here. So BJ is an inversion in alpha, happens if and only if BJ is an inversion in first do alpha, then do gamma. And the net result of this means that the inversions that appear in only one of alpha and first do alpha, then do gamma, appear in this chunk here on these two rows. The inversions have to be something that either starts with this A and goes there. Actually, I guess I should call, well, I'm just going to call it I again. Or it starts with this I and goes there. Or it starts with this B and comes here. Or it starts with this I and goes there. So let's look at that much more carefully. So at this point, what we know is that the inversions that we're interested in are going to be on this part of alpha, and they're going to be on this part of first do alpha and then do beta. Now, what I want to notice, and we're going to just have our I there as our typical thing. So I is somewhere on this row between here and here. Now, A, B, and I, they are simply integers. They're in fact natural numbers. They belong to the set 1, 2, 3, all the way up to n. And they're three distinct numbers, so one of three cases has to happen. Case 1 is I is less than A and A is less than B. Or as a case 2, we could have A being the smallest one and B being the middle one and I being the biggest. And then case 3 is going to be I winds up being between the two. And what I want to do is I want to analyze each one of these three cases one at a time. Because if I can figure out what's going on in these three cases, then we can wind up figuring out how the parity of the permutation first do alpha then do gamma is related to the parity of the permutation that we started with. So now let's look at case 1. Oops, wrong direction. Wrong thing. So case 1 is I is smaller than A and A is smaller than B, and I is living somewhere in this part of the second row in both of these permutations. Now what I want to notice is that this guy here has some pretty important implications. Let's see. Up here, AI is a inversion. And down here, BI is an inversion. So this inversion is in alpha, and this inversion here is in first do alpha, then do gamma. Now, what I also want to notice is that IB is not an inversion up there, and IA is not an inversion down here, because I is smaller than both A and B. So basically, what we've got is we're going to be, when we go from the inversion list for alpha to the inversion list for first do alpha, then do gamma, we're basically going to swap the inversions that look like AI for inversions that look like BI. In other words, there's a one-to-one correspondence between these inversions over here in alpha and these inversions over there in beta. So in essence, these inversions don't affect the parity when we go from alpha to first do alpha, then do gamma. Well, what about case 2? Case 2 was, let's get this back in white. Case 2 was A was the smallest one and B was the middle one, and I was bigger than both of them. And again, I lives on this second row between where the A and the B are. And what I want to notice here is that in this case, we wind up having AI is in order, AB is in order, and IB is in order. No, IB is not in order. I'm sorry, I just made a goof there. Let's go back and look at that. IB is an inversion because I is bigger than B. So over here we have IB is an inversion inside alpha. And what we notice is that when we get down to this permutation, well, the BI is not an inversion, but IA is. And so that's going to correspond to the inversion IA over here in first do alpha, then do gamma. And so again, what we notice is that for each of the I's that are in this part of the second row and satisfy our case 2 condition, we get a 1-to-1 correspondence between the inversions in alpha and the inversions in first do alpha, then do gamma. So these inversions also do not affect the parity when we go from alpha to first do alpha, then do gamma. Well, let's see, that leaves case 3. And case 3 is A is smaller than I and I is smaller than B. And I sits between the A and the B on the second row of our 2 permutations. Now, what I want to be thinking of here is that we have with A and I, that is not an inversion. And I and B is not an inversion. And A and B is not an inversion. There are no inversions, AI, IB, and AB. None of these are inversions in alpha. So in this case, there are 0 inversions in alpha. But when we get down to this particular permutation, well, what have we got? Well, we know that I is bigger than A, And we know that B is bigger than I. Now, I do want to point out, we also know that BA is an inversion, but we only want to count that one time. So we already know that BA is an inversion in first do alpha, then do gamma. The interesting thing, though, is that what we have is that for each of the I's that satisfies this, we're going to be picking up 2 new inversions. And that's going to basically say that we can account for all of the inversions, all of the differences in inversions, by looking at these various pieces. And so what I want to do next is look at putting it all together. So when we go from alpha to first do alpha, then do beta. Well, let's see. The inversions that look like I something, I double something, are unchanged. They're in both. And we also know that the only things on the second row, so when we have A, I, B, and we have B, I, A, this is an alpha. And this is in first do alpha, then do gamma. What we know here is that in case 1, there was the same number of inversions. In alpha and in alpha followed by gamma. And in case 2, there were the same number of inversions in alpha and first do alpha, then do gamma. And in case 3, what we noticed was that for each I that was between A and B, alpha had 0 inversions, and alpha followed by gamma had 2 inversions. And then finally, we have, and I'm going to put it up here, the inversion BA is only in first do alpha, then do gamma. Now let's put it all together and realize that this does not change the parity. That's either even or odd in both of them. This does not change the parity. This is even or odd in both of them. This does not change the parity. That's even or odd in both of them. And now if you have any number and you add an even number to it, well, if it's odd plus even, that stays odd. And if it's even plus even, that stays even. So the net result is adding an even number does not change the parity. And that fact says this doesn't change the parity. So no parity change here. But we have one last thing up here. First do alpha, then do gamma has one more inversion up here. And the fact that we wind up having, that should have been, let's go back. The fact that we have one more inversion means that when we're looking at the inversion number of alpha followed by gamma, what we basically have is a big number with the same parity as the inversion number of alpha plus one more, and that one more comes from the B comma A inversion in first do alpha, then do gamma. And so this guy has opposite parity from the permutation alpha. Well, this particular video has gone on longer than I wanted it to, but I do want to state as an upshot what the final result is. What we now have is we have proven what I'm going to call a lemma, and the lemma is if gamma is a transposition, then alpha and first do alpha, then do gamma have opposite parity, meaning that the inversion number of alpha and the inversion number of first do alpha, then do gamma, of these two things, one is even and one is odd. And that will end this video.